Kammen, who is a professor of energy at the University of California, Berkeley. Professor Kammen also serves as the chair of the Energy and Resources Group and is the director of the Renewable and Appropriate Energy Laboratory at Berkeley. He's originally from Ithaca, New York, and did his undergrad degree, I guess, in 1984, if I remember right, in physics here at Cornell.
Back when dinosaurs were the main topic of it.
Well, when most of us probably, well, not most of us, some of us were still here. And then went on to do a PhD at Harvard in 1988. Following his stint at Harvard, he went to do a postdoc at Caltech, and I think went back to Harvard for a little bit, but then joined the faculty in the Woodrow Wilson School at Princeton, where he spent a few years, and then moved on to Berkeley about 20 years ago, where he has done just phenomenal things. And so we're really pleased to have him here. Now, his research focuses generally in the area of science and technology policy,
Thanks for coming.
with an interest in energy, development, and environmental management. He's authored over 300 technical papers and 12 books, encompassing subjects ranging from the energy, poverty, climate nexus, a very interesting topic, biofuels, photovoltaics, and smart grid standards. He has also helped found over 10 companies, including Enphase, that went public in 2012, and Renew Financial, which also went public in 2014. Since 1999, he has served as a contributing lead author for the Intergovernment Panel on Climate Change. And you remember in 2007, that panel shared the Nobel Peace Prize. In 2010, he was appointed the first Energy Fellow of the Environment and Climate Partnership for the Americas by then Secretary of State Hillary Clinton. He then stayed on to serve as the Energy Envoy for John Kerry and resigned in a letter that went viral. So if you want to know, go online quite recently from that post. Now, it's my pleasure to have him here today, in particular because I think his mom is in the audience. And she was the one who introduced us. And she sent me an email saying, my son is in town, you need to meet him. And this was almost 6 months ago, you get. And I reasoned that, well, if mom is on board, if I made the call, Daniel could only say yes. And he did. So it's my pleasure to have Daniel here. And before he takes the podium, I want to just point out that after the lecture, there's a lunch. And you're invited, as many of you who can attend, to attend, because that gives us an opportunity to kind of, you know, pick his brain a little more, to learn what he knows, because the purpose of this class is to educate all of us. So Daniel, thanks for coming.
Linda, thank you so much. Appreciate it. Thanks a lot. And I know you have to slip out, right, at one point?
No.
Oh, you don't? Oh, wow, okay. Honored. All right. Well, thank you so much. And obviously, I didn't know the Lyndon mom backstory was as strong as it was, but I appreciate both of them for doing this. And thank you all for coming as well. I am going to try to do a mix of the technical inputs, as you'll see, but really focus on some of the output side of what we've done, largely because we're at a moment that I'll get to in a few slides, where we need to move much faster than we've been doing in terms of innovation and implementation of a whole variety of projects. So I'll start off with a short introduction to my laboratory, because the range of projects we're able to do is a function entirely of the students and postdocs who do some pretty interesting and self-directed things. I'll make a pitch, which probably I don't need to make here, but I think you have to make it anyway on a regular basis, about how critical it is that we accelerate the pace of transition to a cleaner energy economy. Not that that should be a surprise to anyone. But I want to highlight what, at least I feel, we're learning about innovation, both in terms of new materials and in terms of some of the new data science tools. And then end that up, and I'm sure I won't get to this point because we're supposed to 1:15, we're done, right? Okay, so yeah, I'll be racing at the point that I talk about what we're currently working on, which is really trying to use the mix of science and technology that we do to think hard about what we're increasingly calling not just the energy transition, but the just transition. So a transition that has equity and inclusiveness built into it in a way that certainly I credit a lot of things to my physics training here at Cornell. I did not learn anything about just and equitable transitions in my regular coursework. Not that they weren't great, but there's a lot more to do. So in terms of the thinking, I'll start off with the laboratory, and it's easy just to start off with a kind of a picture of the team. It's a fairly large, at least by our standards, research group with people from all kinds of interesting places, Navajo land, Chile, Colombia, Nigeria, France, Nicaragua, from the developing country of Washington, D.C., and all kinds of various spots along the way. And as Lyndon mentioned, I've been running this lab at Berkeley now for 20 years. I moved there from Princeton, and we set it up, and a lot of the initial work was on both detection of climate change topics and increasingly on sort of the role of what was then very expensive technologies, solar and energy storage, variety of features. But we did get to work on a whole variety of aspects of the IPCC, the Intergovernmental Panel on Climate Change. And as you heard, we got to share the 2007 Nobel Peace Prize, which was pretty cool, pretty great event. You got this great plaque. But as all of you know who read the books about the Nobel Prize story, in particular the book Losing the Nobel Prize, only 3 people can win a Nobel Prize. That's the law. And that means there were several hundred of us that were involved in the IPCC at the time. And so you get credit for it. You don't get the check. But more importantly, certainly at Berkeley campus, and since I drove here today from Syracuse and was prevented by your high-quality gatekeepers from getting onto campus, I think you have the same problem we do, and that is that there is something more valuable than the check on an academic campus if you get to be part of a Nobel Prize team, and that is parking. And at Berkeley, anyone who's visited knows that when you drive around, you see parking spaces with a big, huge NL on them. Nobel laureates are the only parking places that are inside campus. And so pretty exciting, and Berkeley thought about it. There were 4 Berkeley faculty who were part of the effort, and so we thought we're going to get parking spaces. We were like, rubbing our little hands together. Inez Fung, who some of you know in atmospheric science, Kirk Smith, who does public health issues, and Bill Collins, who does mesoscale climate. And so we were really kind of licking our chops about that. And Berkeley did, 9 years later, finally come through in a very Berkeley way. We did receive parking space with a big NL on it. It's bicycle parking. And if you read the fine print, parking not reserved for IPCC contributors, all cyclists welcome. So it was a very Berkeley-esque response, and so, Berkeley does its thing. But so our lab has been involved in that, and we've been involved in a lot of non-physics, non-engineering things along the way. I can only describe this best as financial engineering. We worked on and came up with an idea to basically help cities lend money to individuals, businesses or individuals to invest in energy efficiency, solar projects, a whole variety of things. And I'll come back to both the good side of that and the bad side later. It works great. It got lots of press. It's now called PACE. We tried to call it Berkeley First. That name didn't really translate well out of Berkeley. It's now called Property Assessed Clean Energy, an investment mechanism that's used in a number of states, and it's done pretty well. And over the last decade, and the thing that I'll spend more time in this talk talking about is that we've started to build really data-heavy models of current power systems around the world and chart out what they would need to do to transit quite dramatically to almost entirely decarbonized ones. And so some of our current projects with China, Morocco, Kenya, and Malaysia are part of this kind of mix. And it's part of a bigger collaboration. So our lab has a whole variety of community group partners, some nonprofits. We work with a number of businesses, and I'll come back to the projects with Google in particular. Nitel is a microenergy company. Virunga Power is the energy offshoot of Virunga National Park, Africa's oldest national park. And then the nations for which we've built these models are the ones shown here, and I just put California down because we can never figure out if we're a country or a state or not. So it's confusing to us and to others. But we do this because we've really had this huge range of students who've gone on to very disparate jobs, from President Obama's science advisor to the first person to have held both the California Public Utilities Commission that basically sets the rates and laws, and also commissioner on the Energy Commission that decides who gets the money. Majid Azati was one of my early students who's now director of epidemiology at Imperial College. So a really interesting and diverse group of places they've gone to. Grad PhD students there, master's students, and some undergrad examples here. And so all the things that I'll try to run through, you can get both on the website of the laboratory, Renewable and Appropriate Energy, Berkeley EDU, and then the Twitter. We try to do kind of one tweet a day about the things the lab is up to. So let me jump into the energy systems transition story. And just because of all the great stuff doing here, I'm not going to spend time making the argument why we need to sort of adjust our climate system. I won't do the climate history, but I do want to remind us kind of where we are or were or are going, depending how pessimistic or not you are about making good on the Paris Climate Accords. But basically, the agreements that went into the Paris Accord would take the global trajectory from warming by over 4 degrees Celsius to, if everyone did what they promised in Paris, we would cut about a degree off that total. Amazing start, not as far as we have to go, but a really good start. So this is what everyone's committed to. And the sad story is that we're now 2 months out from the COP24 meeting in Poland, and only one country is on pace to meet the 80+% decarbonization that they promised. And since it's so odd and surprising, who knows what that country is? It is not Denmark. Denmark is behind schedule because Maersk is 40% of Danish emissions, and they do not have a solid plan. The one country, good guess though. Nope. Iceland has way too many overseas financial holdings in places they don't control the emissions. It's a good question. It is Morocco, the only country. So it's an African country. It's the only country on pace. And Morocco has many challenges, but they have the most successful large-scale renewable energy program in place so far. Now, lots of things can go wrong, but there's a lot interesting in that statement that Morocco right now is the leader. They're the only one who was rated out as fully on pace for their 2050 goals. The challenge, of course, is that many of us are not on pace, and that would only get us just about halfway to this 2 degrees C or less target, recognizing that we've already warmed by 1 degree C. So we don't have a lot of headroom left. So this is the needed innovations part of the story. And one very interesting piece of science and policy that doesn't get a lot of attention is that in the excitement after the Paris Accord calling to keep us under 2 degrees C, I'll get to the 1.5 in a second, but under the 2 degrees C, Secretary Kerry, my former boss, was the lead in the US on getting the Kigali Accords passed. 6 months after Paris, everyone signed on to a second round, largely industrial emissions and from refrigerants, and that would cut off about another half degree. So the things that we've now promised to do, but arguably only one country is really on pace for, would get us more or less halfway, with the complex story that 2 degrees obviously was going to bring us down to very close to zero emissions. And the next thing, of course, is that now there's this excitement around the 1.5 degree targets, and I'll get to them in a little bit. But what that means is that you have to think about first bending the curve to get us off of this growth path, and then think about bending the curve negative. And those are inflections that are hard for physicists and engineers to see happening easily, but we have some interesting data, right? In California and the United States, this is electricity use per capita. And if we look at the California and the US, we're more or less growing the same. The OPEC oil crises happened. Different parts of the US adopted different strategies in terms of thinking through clean energy transitions, what we might do differently. California, through a series of different measures, by developing a state agency, working with university groups and industry to double and triple down on efficiency for industrial, commercial, and residential buildings, have done this remarkable transformation. So electricity use per person in California has stayed flat for decades, despite all of the incredible proliferation of electronics. That was something that I won't say my economist friends, because if I say it this way, I won't have any anymore afterwards. But in the 60s and 70s, you could not find a mainstream economist who said it was possible to decouple growth in energy and have GDP keep going. And so this is a remarkable statement. Of course, I'm cheating a little bit because I've said twice that this is energy use per person, right? But of course, California, like a lot of places, has a lot more people than we used to. So per capita is great, but when you grow your capitas, it doesn't mean our total energy budget is flat. It means that we've done remarkably well per person by investing in efficiency. And some of the things that have come out of this process are not just kind of better windows, better HVAC systems, lighting, a whole variety of things. There are things that we passed that were derided at the time as impossibly aggressive, and now for anyone under 30 or 35 will seem mundane. So in 2006, one of the things that we got through the Energy Commission and then the Public Utilities Commission in California was a requirement that after 2020, we can build no more homes that aren't net energy generators. And that was, was seen as a huge bet on efficiency and largely rooftop solar, although if you're in a rural area, it could be rooftop wind or nearby the barn wind or whatever else. But this took us, oh, didn't work quite right. This worked. California passed this into law late 2018. And so now every home in California builds still a lot of homes, almost 200,000 a year. All new homes have to be net energy zero by 2020. And again, this was seen as impossible at the time when it was written, but now, again, many of you have rooftop solar. Yes?
Yeah, can we just, on the scale of kilowatt hours, is that electric only?
What's that?
California case?
Do you mean this or the?
Previous slide.
So actually,
Is this electricity only?
it's complicated. When it was first done, it was electricity, but now it's total energy. And so it's a bigger bill. Includes transportation, but it does not include industrial use of energy that doesn't have an end use in state. So if you use industrial energy to do export products, they're outside the scope of this right now. So that gets to a much more complicated story about international trade, which I will do nothing on during this talk. Apologies. So this is now law in the state, and since we build in the order of 2 million homes nationwide a year, if programs like this were to scale, that would be pretty gutsy. At the same time California passed this one, we passed another one that we kind of snuck in there. And we knew how to do the first one, but the second one, all office buildings, irrespective of height, by 2030 have to be have to be net energy generation. We do not know how to do that today at all. We're hoping the next 10 and a half years will, 10 and 3/4 years will make some serious innovations. We need those new batteries like today to get there. But I would say that half of my academic friends in California and people at some of the companies would not have pushed as hard as they had done without having this in place. And so this kind of interesting back and forth between what science can do or what we don't think we can do yet and what we're requiring is an interesting part of the story. Of course, California's clean electricity mandate went from 20% in 2010 that we missed it by a few years. We hit our 2010 target in 2013. Our 2020 target is 1/3 powered by renewables, and we are already about 36%. The estimate by the end of 2020, because we always go to the end of that year to give all the time, will be something like 37 or 38%. And the 2050 goal was 50%, but then we passed Senate Bill 100 that requires 100% clean energy by 2045 and upped the 2030 target to 60%. So it's an interesting set of kind of doubling down on what we think we can do, but also passing some regulations for things that we don't know even today how we're going to get done. And there is some subtlety in here. These are renewable energy standards, but this says clean energy because we have not made peace yet with large hydro or nuclear. Right now in California, neither big hydro or nuclear counts in the target. California's down to 1 nuclear power plant, Diablo Canyon, that's going to close now in under 8 years, which means it's closing 3 decades early. And this nod to clean energy is because there's a lot of uncertainty in how we think about this. And if you saw the first slide, I am a faculty in the Department of Nuclear Engineering, although the piece of it which I am likely to dedicate a lot of the next part of my career to will be nuclear, but fusion.
Is this consumption or production?
So this is consumption-based, and it's quite a bit complicated because we also have tensions over electricity generated in state versus out of state, but it's what the utilities must procure to meet demand. And then there's a whole second issue about the credits you get for in-state generation versus out of state. But this is on the utilities. Of course, one of our utilities is now going bankrupt, and so who knows? So that was a very quick bit in terms of how I often think about these things in terms of California's path to try to meet these kinds of targets. And the piece of it that I glossed over, but should not be glossed over, is that now that 1.5 degree C is on the table, you saw how close to zero net emissions the 2 degree path is. That means that most of the scenarios that we look at in terms of IPCC work and many states and countries individually gets to negative emissions in small or very significant amounts by sometime mid-century. And that opens up this incredibly complicated and sort of broader and more interesting in some ways process to think about electricity, also about heat, but also about how do we manage our food systems, our land systems, so that we can achieve this without essentially destroying the remaining parts of the planet that we'd actually like to preserve in the process. So it's an interesting, kind of much more complex picture, and it's why some of the projects on everything from biochar to some of the most aggressive smart agriculture projects to some of the forest conservation efforts now have a much different seat at the table than they had even 5 years ago in terms of thinking about the climate story. So I will not delve into it in too much detail, but I want to mention one case that we worked on that, in my view, kind of highlighted how much those policy objectives are critical, but if you don't build good enough analytic, material science, technical capacity, you can really box yourself in. And so I'll do it very briefly, but as the world, or as I should say the world, as the US was getting excited about biofuels in the late 90s and early 2000s, we ended up building a life cycle calculator tool, and it's really this point that I learned life cycle analysis in my kind of evolution, so that we could compare all of the different fuels, fossil, biofuel, and non-liquid fuels, on a comparative basis. And so we built this whole calculator tool. It got a lot of interesting attention at the time in terms of some people liking it, some people thinking we'd given short shrift to their favorite fuel along the way. But what was interesting to me looking back on it is that we did this right at the point that California and the European Commission were trying to think through how do they both quantify and regulate all of the different fuels for transportation they will use. And so we built this model, made it freely available, and interesting little detailed sentences that we put in to be technically correct, but didn't think they were going to be the core of the story, ended up being critical. So life cycle calculators, we looked at the energy to make fuels, to grow biofuel crops, the energy to make the equipment, et cetera. And a small part, kind of a footnote in the article, became the whole story. California adopted our model within the first year. We ran this model called EBAM for all fuels in state to quantify them. And what came out of it was something called the low carbon fuel standard. California basically said the same way that we rate electricity, we're going to rate fuels for transportation. Gasoline was our reference, and it's about 94 grams of CO2 per megajoule. And that if we look at Midwestern grown corn, so corn that has the kind of the typical mix of fertilizer, fossil fuel-based fertilizers in irrigation, if you just look at the blue, you get the direct inputs to the life cycle analysis. Brazilian sugarcane, quite a bit better. Why California grows ethanol, it does not make sense, but they do. These were the fuels that were of interest to regulators at the time. And at the time, we only built the blue bars. That was the direct life cycle analysis like you do in kind of civil engineering types of processes. But what came out of this one little sentence in the paper was the recognition that if we stop growing food and start growing fuel, or if we expand land use for biofuels, then there is a signal that's through the market. It's not through the direct life cycle of making the tractors and growing the crops and putting fertilizer on. And this is the controversial, still to this day, part of the story. The green in each of these graphs is the indirect land use signal. And that means that if everyone in the front row is a farmer, one of you grows only on your organic farm wearing Birkenstocks, and you never have any sort of other materials, everything is wonderful locally. And you over here are a huge industrialist owning 2/3 of Midwestern states I won't mention, and you buy lots of petrochemicals. Each of your decisions may look different politically, but what happens in the global food and fiber market is something that you don't have a direct control over, whether you're thinking you're super organic or you're doing, kind of some traditional fossil fuel intensive agriculture. And so this is what we calculated with our partners at Purdue using the global, it's called the GTAP model. It's a global trade model to look at the impacts. California chose to adopt those numbers as the additional impact of these choices, and some of them are quite interesting. There are parts of the US where corn is grown with almost no external fertilizer or irrigation, so very small. But there's also places where, because we're converting corn production into biofuel that used to be for food, that we're now seeing huge expansion, whether it's soy or corn in the Amazon and elsewhere. And there are places where tropical forests are being cut down, and you would need to grow that crop successfully for hundreds of years, on the order of 300 to 400 years, to pay back for all the carbon you lost by cutting down and deforesting and changing the ecosystem. That's why this unobservable green continues to this day to be very, very controversial. California, finally the European Commission and the EPA under a prior, happier administration, also adopted this. And so this low carbon fuel standard has been the way that a lot of places look at this process overall. And because biofuels, for many of these problematic reasons, are no longer as popular for transportation as electricity from cleaner and cleaner sources, this low carbon fuel standard also provided the way to quantify the metrics for electricity, if it's being produced by wood waste or we're doing hydrogen, a variety of things. And so that's the way that we assess our fuels. And right now, electric vehicles are getting all the attention, but in 10 years, maybe it's hydrogen, who knows. And we battle onward to this day. So just recently, the European Commission was presented a proposal to count any biofuel imported to Europe in any form as carbon neutral. Biofuels grown within Europe, they have to apply this metric. But if you ship in wood from South America or the US Southeast, which is a big provider, it doesn't have to go on. So we've been battling away, and there's been like signing ceremonies and 60 Minutes episodes to kind of battle through this story. The Guardian is tracking the degree to which the European system should really account for these kind of impacts. And I spend time on this long example, both because it's interesting in itself in terms of thinking about how you do the quantification for different biofuels in the economy, but also because it led us to think, in my lab, much more broadly about energy systems, and so to go on from that effort around life cycle analyses of fuels for transportation to look at power systems much more broadly. And so what I want to spend a little bit of time on next is a model we started to build 10 years ago. It's called SWITCH, which roughly stands for solar and wind integrated with transmission and conventional sources. And SWITCH is a big linear program. It's a model of the power system. We started by building it for California. Then we built it for all of Western North America. And now all of the places in green are official partners of the lab, where we have university partners in country, and we have at least one government office that talks to us. They don't always listen, but at least talks to us about the efforts. So after we built the West North America, we built it for Chile. We built it for Nicaragua. Mexico will come online later this year. East Africa is building a regional power market modeled quite a bit after their experiences studying what's going on in West North America and the PJM network here. And so we've currently built and released models for Uganda and for Kenya, and we're working on the others. We finished Bangladesh now a bit over a year ago, and the biggest team, and I'll come back to in a bit, is looking at the Chinese power market. So this is a very classic linear programming project. What we do, I'll only spend a second on the math part, is that what we just do is we minimize the net present value of all investments in the power sector. So all existing power generation plants and all transmission projects. And then we look at all of the fuel costs for current plants and what new transmission or upgrades we would need to build to bring on new plants, whether they're large nuclear or solar plants in the desert, whether they're new natural gas plants. And we basically analyze all of that. We look at the capacity factor for each plant. We keep a reserve margin. Different parts of the world have reserve margins, meaning extra generation capacity. Some places it's negative, like Nigeria, not so good plan. Other places it's 5 or 10%. In Western North America, we have a reserve margin of around 15%, so generation capacity that could be brought online. And we do this in a large programming tool where we look through what would be the scenarios. And so just kind of to jump to an output picture, if all of West North America were to meet that 2050 target of being under 2 degrees, this is what our base case looks like. And just to kind of decode it, the black line is a forecast of demand. It's one scenario of growth in demand. The colors hopefully are representative. Light blue is wind, dark blue is hydro. Yellow here is solar. This is gas with capture, whether it's biogas or natural gas. This here is geothermal. This incredibly thin line of purple is nuclear. And then these negative going spikes are energy generated in the mix that's put into storage and then is brought back out. And that storage can be both central station fixed plants, large battery systems, pumped hydro, compressed air underground, or electric vehicles if they are smart and vehicle to grid connected, so that when you're not using it, the battery can be used in the system. And so I just want to highlight this picture because anyone who's a power systems expert in the room, who's my age or older, this is a new world, because in the old days we thought of the world as largely powered by baseload generation, kind of very steady, maybe some scheduled downtimes. And almost none of this, all this kind of crazy noise, is the new world of energy where we have to deal with very intermittent sources, the solar and the wind that go up and down, and hence the need for storage to be integrated centrally to the story. And so we build scenarios like this for all of those countries that you saw listed there. And just to kind of walk through an example, this is the scenarios that the governors of the states in Western North America, in the US side, and Alberta and British Columbia. Alberta is an observer. I don't even know what that means. British Columbia is an actual partner, and then Baja California, Mexico are all partners. So all of these scenarios here are ones that were either dreamed up by us or requested officially by the partners. And hopefully they kind of make sense. So the reference scenario is the one I just showed you. And then we have scenarios. Sunshot is where solar becomes actually as cheap as it's in fact become. And if batteries also become cheap, there's another scenario there. If solar is cheap and batteries are cheap, this is my favorite personal scenario. That's this one here. If nuclear prices are what they were at the end of the US construction, we haven't built a plant since '96, and we use CCS, there's a case here. If we decide to throw away energy efficiency, I don't know why, I won't say which state requested a low energy efficiency state. It was a state that hadn't done much on it. But all of these are kind of different versions. They all get you to that 2050 target. The problem is, of course, that some of them require you to build lots of transmission. Others require you to build lots of distributed generation sources. And so while the scenarios are really illustrative of where you might go to get there, they don't actually tell you in the end as much as you would like. They're helpful, but if you want to go strongly into large-scale distributed solar or wind, you need to build transmission to get it online. And since building transmission is as painful as building nuclear plants in the United States, for example, you have to really do things in advance. So an interesting kind of, you probably didn't need the model to know that, but if you optimize where you would, for example, do a nuclear-heavy future, an interesting feature is that you'd have very little other costs, because basically anywhere in the US where you have a current coal plant, you probably have a reasonable supply of water, and so dropping a nuclear plant in there means you can more or less think about a plug-and-play kind of swapping these in and out. However, nuclear is not doing so well for a variety of interesting reasons. CCS, in my view, does not exist as a technology. It exists as a practice in the lab, but there is no large-scale CCS. Current US CCS is essentially the Decatur, Illinois ethanol plant, 1 megaton a year, and we need to be on the gigaton scale. So it exists on lab. Some people may disagree here, but I would say this scenario, you should put quotes around it at best. And so thinking through the investments you need, both in terms of research and in terms of planning to make these work, is a really big story. And it's partially why this is my personal favorite, but that doesn't mean much. And it also means a really interesting mixture of where you build generation and the transmission lines you need. And so again, the colors hopefully kind of make sense. Some of them are hard to read down here a little bit. But so for example, if we go from 2020 all the way to this very decarbonized 2050, we're in a world where we have lots of solar on the west and the south, no surprise. We have hydro in the places where we have a good supply. We have wind in the middle of the country, and then a mixture of geothermal and, again, heavy amount of investment in transmission to bring this all together. And so we kind of build these kinds of pictures for all of those partner countries. And that gives you a picture of how we kind of think through the technologies that we have today and reasonable amounts of evolution. So everyone in the room who studied solar in detail has seen this incredibly complicated graph. Because NREL, the National Renewable Energy Lab, produces it every year, and this is showing you the efficiency of solar cells. This is, I think, the most complicated graph I think I've ever seen in some sense. But the colors code different types of technologies: single crystalline cells, multi-crystalline cells, amorphous solar, interesting emerging technologies, perovskites, quantum dots, organic solar cells, all showing the unit, university, or laboratory, or business laboratory that had the record for the maximum efficiency at any given point in time. And if you put it up this way, it kind of gives you an interesting picture of what's going on in the field, right? At one crude level, this is efficiency versus time, so the slope of this is somewhat interesting. Doesn't tell you the whole story, but it at least shows you that some of these older ones have progressed pretty steadily. And while these new exciting technologies are not as efficient as the old standbys, at least the slopes are higher here. Of course, you might also ask things like, well, does actually the efficiency matter, right? Aren't we really more interested about cost and survivability over time? So there's lots of interesting metrics. But analyzing these kinds of trends, industry by industry, has gotten us all kinds of really interesting insights that we then put back into models like that switch model I showed you. So just to kind of highlight before we go on to that kind of thinking about technology evolution, what's going on now in solar is as revolutionary as it was kind of a few years back. So the neatest new things that I look at are, I work with some colleagues on some transparent solar materials. So you can think about office buildings where you have actual windows you can look through, which is good. And they're also generating power. We just hired 2 new faculty at Berkeley who are doing fabric integrated solar to power your devices. Someone's going to get a shock at some point. We'll leave that. But powering up all your personal devices, not with old clunky things like solar panels, strapped into the back of the jackets, as was very popular in certain movements. But now integrated materials, photovoltaics, kind of a new trendy thing on the horizon. All of these kind of illustrate some of the neat things going on in one of these areas. And so a whole range of people in operations research and economics have been looking over time at what has this level of innovation given us in terms of improving these technologies, in terms of lower costs, but also in terms of performance, because this goal of 2 degrees or 1.5 degrees is going to require some really dramatic changes to get there. And so the basic story over and over again, even if it really doesn't appeal to many of us, has been the classic picture of the learning curve. Right? The idea is that if you look at the data I just showed you, look at the level of innovation, it would be nice if the cost in the future at, say, C2 versus C1 followed some simple form. And it turns out that that simple form appears again and again. And that is, if you look at cost, it's in log scale. So this is cost not versus time, but by total deployed volume of technology, not just built and left in a warehouse, but installed in the field. We see this wonderful power law where the slope of this line is essentially showing you that rate of innovation, right? So this is showing you cost in the future as a function of the volume of production of that product. And I have never liked this. I've always felt this doesn't capture any things I want, but technology after technology, we see this appearing again and again. These learning curves for solar, it's about a 20% consistent over decades reduction in cost for every doubling of the amount of solar. It's about 13 or 14% for wind. We have a whole variety of these. And so I want to talk a little bit about that in the last part of the talk to kind of highlight what's going on. And so when we look at this innovation for decarbonization, how can we both learn what it takes to make these technologies not just cheaper, but also better, more reliable, longer lifetimes, et cetera? The pushes that we've seen in the solar and wind areas in particular are dramatic. And so recently we had solar installed in Saudi Arabia and then in Dubai at under 3 cents a kilowatt hour. And I got calls saying, oh, it's not possible. You know, they must have cheated in some way. Just recently we had solar come in at under 2 cents a kilowatt hour at large scale. And so these learning curves are interesting. We're seeing this progression. And if I were to put up an older curve of learning curves, here's one. Just don't look over on the right for a second. So NOx controls, I mean, you scale up, wind, solar, I mean, the slopes aren't exactly the same, but there's a lot of interesting information in here. You know, we need to think hard about, you know, if these are learning curves, I don't even want to say, as a professor of nuclear engineering, what I would have to call that a forgetting curve, I guess, or something. But this gives you a really interesting picture of what's going on. And if we look at the area that I've been studying most intensively recently in terms of this kind of, you know, sort of techno-economic perspective, this is the current, as of 2017 for batteries. And so lithium-ion batteries are on here, nickel metal hydride batteries, lead-acid batteries are on here, flow batteries are on here. Interestingly enough, you know, they kind of show the same shape curve. And of course, the two exceptions to the rule are pretty interesting, right? So here we have pumped hydro. Shouldn't be too surprising that pumped hydro hasn't seen the same kind of cost decline for manufacturing, because pumped hydro is pretty simple. If you have the right geography, you pump water uphill. Pumps have not changed much. It's a function of, you know, potential energy U equals mgh. So the learning hasn't seen a whole lot in the last several decades. And then interestingly as well, lead-acid batteries haven't also seen a lot, because lead-acid batteries are not super useful for these new types of devices. The big push for better lead-acid batteries were vehicles designed to give you a starting jolt, not to do long-term powering and things. So these two exceptions are quite interesting. But all of these with different slopes show kind of similar types of behavior. So, you know, I'll tell you in a second why I really don't like the idea that this simple heuristic works so well. And I don't like it because I would like to have thought from sort of first principles that we needed to know more about the investment in research and deployment and various things to get an understanding of how these technologies are evolving. But those curves are fairly compelling. So what we've been doing the last 2 years was to take this as a starting point and start building a little more complicated models. And so the one that shows the best fit to data so far is one that appeals to me greatly. And that is, Our now two-factor learning curves have the traditional term due to the volume of production, but they also have a measure of R&D. And in fact, this is the best fit. I won't go through the details here, but the best fit for the solar and the wind and the energy storage data is not that old one-factor curve, but it's two-factor curves. So I would regard that means that I was pretty excited when we did this. In fact, it got my student a pretty neat job as a result. But I actually want to highlight to you why this is kind of problematic. It shouldn't surprise you if we just drop this term, why this model, A, it fits the data pretty well. B, it's also wonderfully easy. You can measure quite easily the total volume of manufacturing and production of materials. So if we just drop this term, right, set alpha to 0, it's compelling in terms of the real world, in terms of thinking things through. We find a better fit if we also include a term measuring R&D. Now, the way we measured it is, in this case, to look not at dollars spent, but we used patents generated as our metric. And lots of interesting things go on when you do that. One is, of course, that patents are not always designed to move the field ahead. A number of patents are defensive to block others, and so patents, no question, are a poor overall predictor. And in fact, not to get into the stats, but we find that the fit is better not just because we have a second variable. So we actually find the fit is significantly better by doing this than you would expect alone. However, what measure of R&D should we use? We use patents because that's a data set that's available, but I've got students chasing a whole variety of other measures, and one of them just proposed to us 6 months ago at a big summit we had around this with Google was actually that they argued that we shouldn't be using patents or dollars spent on R&D. We should be using the metric of students that did not complete their PhD, which really pained me, right? But the argument made was students that get their PhD, I guess advisors in the room and students shouldn't listen. If you get your PhD, you're going to often do what I did, go be an academic and be semi-useless. But if you drop out of the PhD, but you stay in the field, you're going to put your PhD to use in an accelerator and starting up companies, and you're actually a kind of a valuable member of society, as opposed to what some of us do. So I've resisted that measure, but I highlight it because one of the things that I think we critically need to do is to think through how do we understand and value R&D, not just because we like bigger research contracts and grants, and we do believe that it spins off into companies and useful things, but with this era of kind of fake news and this complete disrespect for science and engineering, it is clear that if we can do a better job of understanding this more intricate form, we can actually do quite a good job of highlighting what is the value of what many of us in the room, maybe all of us, think is a valuable part of the process. And so we've been, again, working with patents right now, but I would argue there's lots of other metrics. I'm loath to start gathering data on the dropouts from the PhD programs, but I suspect Google's going to give us that data whether we want it or not. One of the examples of combining this story together is that we use the switch model to examine those scenarios that I mentioned for Western North America. And in terms of these negative going spikes, we convinced the state of California, largely because they paid for the model and they are the biggest consumer of energy in Western North America, that we were going to have to dramatically accelerate both R&D on batteries and storage, but also deployment. So some of you, anyone in the room funded directly by ARPA-E? Really? That's interesting. Is anyone in the room, who knows what ARPA-E is? Okay, so ARPA-E, the Advanced Research Project Agency for Energy, I thought half of you would have been ARPA-E funded. Used to be, okay. It means you moved on, all right. This is an interesting conversation, by the way, right? So one of my students ran the energy storage program, someone named Elon Gurr, who after his term running it came back to not Berkeley, but to Lawrence Berkeley Lab, where he now runs a clean tech innovator, a startup accelerator called Cyclotron Road. So This scenario requires a lot of storage, and so we worked closely with the prior governor in California, Governor Brown's team, to argue that the model said clearly for all of those scenarios, essentially, we needed significant amount of storage online. And the R&D pipeline is doing pretty well. Thank you guys for working on it. But we needed more storage in place. And so we passed a law 4 years ago that said by 2020, California must have storage available to meet 2% of peak demand. And I won't get into the fact that some people apparently don't understand the kilowatts and kilowatt hours are different things. This is complicated, but it's why we started off with a mandate not based on duration of storage, but on peak capacity. 2% by 2020, and right now we're working on a storage mandate for 2024 or 25 that will be somewhere double that, 4 or 5 or 6%. And this is a physical version that came out of our first mandate. So Southern California Edison, it's not in bankruptcy, contracted with Enervault to build a flow battery system powered by PV because you can't be powering it with fossil if you're going to get the benefits out of the story. So here we have a facility. It gives you a quarter of a megawatt of capacity, 4-hour duration, and they're using it in the mix in the grid. And so we are hoping that as we get the 2024 mandate rolled out, that has to be rolled out by the end of 2019, to give industry enough time, that we will have built up more storage capacity in California. Germany has a similar feature, and China is working on one that I'll talk about at the very last minute. But one of the interesting features that's come out of all of this technology mix, not just for California, but now we're starting to see it in parts of eastern China. We're seeing it very strongly in Australia, that has the most rooftop solar per capacity. Any Australians in the room? You should be proud. You should be proud. I mean, what's going on in Australia, for all the challenges over water and cooking fish in the oceans, solar, doing great. So a number of places are coming up with a challenge, which is looking more and more like this. So this is, for anyone who works on Western grid issues, this is the famous Duct Curve. And so this is time of day, and this is the overall net generation load. And so, of course, most of us, except for students, are supposed to be asleep during this period of time. So demand is lower. And during the day, solar comes online. So if you have a lot of solar, you start to hollow out the demand curve. But then we heard the sun still sets and that kind of stuff. And so at the end of the day, you get this challenge where the solar generation is going down and demand is highest, or used to be highest, because industry is still on and people are coming home, so we have the maximum amount of stuff turned on. So you get this evening peak, and then you get this horrific ramp rate. And that's why we built the switch model, to understand how much generation, how much storage you need, so that this doesn't blow out all your transformers and your system doesn't work. So interesting mix, right? So one of the features is that we want to double, triple, quadruple down on solar and wind to really maximize our generation. And so we have forecasts that our generation in the peak generation times in the afternoons could be so large that our overall demand curve has been completely eroded away. There's very poor business model for industry because of all of our rooftops are generating power. And then we critically need all this power to come back online, right? So one of the things that we were doing in California, which has a mandate to have 1 million electric vehicles on the road by 2020, we probably won't get quite there, is to start thinking about what mixture of that central storage I just showed you, plus our vehicles or storage in the basement of your home or your school or something, could be used to smooth out and basically bring the power to this kind of peak time. And it's this kind of use of the models that's gotten so interesting. And it's gotten particularly interesting, of course, for the EV reasons I mentioned before. And so I think I use 350 a gallon on here. So at 350 a gallon, your vehicle is running at 14 cents a mile. If it's a more efficient vehicle, be it hybrid or just more efficient, half that. If you're using solar from the grid, and I used California prices here, you're driving at 3 cents a mile. And at that 1 cent that I showed you before, you're driving at 1 cent per mile. So at the point that the cost of the vehicles, their performance gets comparable, you don't find many situations where you have more than an order of magnitude difference in the operating costs. And since now we have EVs that are remarkably inexpensive, BYD, a Chinese company, just announced a $9,000 electric vehicle that has 70-mile range. The average American drives 40 miles a day. So going from the fanciest Tesla or Pritzker or whatever else, it's a remarkable story. And it brings me back to what I began with, and that is, of course, if we look at just the United States, this is the mile per gallon of the same electric vehicle across the country based on the mixture of clean or dirty fuels, right? So places that have lots of hydropower, no matter what we think about what it's doing to salmon, hydropower, whether it's in New York State or taken from the Cree Nation in Quebec. So you get this interesting mix where that same EV is worse than a hybrid vehicle in some places and incredibly better in others. And of course, every time you clean the mix, this number goes up. And so Texas, which has just announced new mandates, you get this kind of remarkable changes. And now that Tesla and others are thinking they'll have these amazing vehicles on the road, 500-mile range, charge it up in 30 minutes if your batteries won't blow up. We've got this kind of interesting picture. And so China has just announced that they are now in the planning process using our switch model and then the model run by NDRC. There is no NDRC, it's hard to describe. NDRC is the National Planning Agency, and it rolls many different features into one mega company. So China is now in a process in this conversation with us to plan first the phase out of manufacturing of internal combustion vehicles. Right now, they're the world's largest producer. So the phase out of manufacturing is following what's happened with Volvo. Has said that after 2021 or 22, no more combustion vehicles. Ireland and France have also said they have plans. But China has now said no more internal combustion vehicle manufacturing after sometime in the 2030s, and no more combustion vehicles on the road after 2040. And so our switch modeling team is really busy doing those scenarios. And we're working on all kinds of things like mobile charging pads. You don't move the cars in the garage. The charging pads move between vehicles. And of course, my current favorite, and that is inductive charging while you drive. And so in Sweden and in the Netherlands and in 2021 in North Beijing near North China Power University, there will be high-density roads, highly used roads, where there's a lane where you can recharge inductively while going. And so this is this interesting collaboration. There's NCPU, the university that's installing that first section of road there. And just to give you a feeling for how envious I was of the data, this is the electric vehicle control room in Beijing. This is the 2.3 million EVs on the road, the 279,000 charging stations. And just because I walked in, they flipped the control quickly, and they put up the US, EU, and Japan just to kind of embarrass us in terms of numbers. But it's a really interesting overall process. So I've highlighted in kind of this mix the range of how these kind of technology models, I think, have played a critical role in thinking through how you set standards and how you try to plan your investment in the various technologies. And I hope that I know that we're right at time, and I hope that the most key lesson was not that these models tell you what to do, but if you can work on both the information generation side and on the implementation, you can really accelerate the process, as I think we've seen in some of these places. So thank you all very much.
Thank you. So we can take a couple of quick questions. So in your, so I was curious about your learning curve model. So what does alpha look like relative to B?
Yeah. So again, if you drop this term entirely, the classic learning curve has a power law, so that slope is like negative 0.2. We see that roughly that 20% learning here. What we find, and again, the metric you use is critical because measuring innovation is something that none of us can do, right? So if you use patents, and in the data we have for batteries, where we don't have as much data yet of people who clearly patented to block others, Maybe that's going on, but we can't find a lot of evidence of patents that were worked on, the patent was generated, and then the company or its spin-offs did nothing on it, which is the classic economic definition of a patent that was to block others. We don't find a lot of data on that yet. If we do, we'll change it. But what we find is that this explains about 60 to 70% of the behavior, and this is that 30 to 40. And again, if I had walked in here and said, R&D is not important, and I think that, the color of your rooftop is important, some other metric, right? Who knows what we would have found? So I think I can't guarantee we picked the best second metric, but the fact that it explains that much of the behavior, and it does better than just simply another dummy variable to explain we're doing pretty well. So
A is about 0.1-ish?
about 0.1, 0.15 is what we find right now. But no one has good data on, almost no one tracks investment in R&D in easy to digest ways.
And there's a lag. And so
Exactly,
I think
right.
there should be a phase lag, maybe a sign.
Right. So we did, so our first paper on this was in 1999 when we first tried this out. And we built a model where we looked at just patents, and we assumed that that dollars would flow, and then patents would go, so there would be a lag.
Yeah.
What we actually found was that patents preceded dollars spent. And the only explanation that's sort of held up in the conversations is that in areas that were new, university researchers and those at big laboratories had work they were working on, because we all know we do shuffle money between grants a little bit in terms of supporting people, and that if you know there's going to be a new call, people get their new products out so they can. And so we haven't followed up on that since, but in the push of R&D data that came largely from the Carter efforts, there was clearly the patents came before the spending. So tricky.
So one other quick question? Yes.
Yeah, thanks for your talk. The 2030 commercial building standard in California, will the owners be allowed to build that generation off-site, or does it have to be part of the building?
Ah, great question. So when it was initially written, let me go all the way back to it somewhere here. When it was initially designed, we were thinking entirely your building is the footprint. You put solar on the roof, you put a battery in the basement, you do energy efficiency. Because this only passed into law less than a year ago, industry, of course, blew up. They said, wait a second, we didn't know we had to start building all of these net zero energy homes, even though net zero is a terrible term, but we'll leave it for now. And so there's been all these interesting pushbacks. Some of them have been lawsuits, they're not so fun, but the interesting ones have been companies that said, well, look, we think we can do it, but exactly what you said. There's no reason why the generation needs to be tied to the site. And so one of the largest supermarket chains in California, called Safeway, has already committed to own 100% renewable energy, which they buy from off-site. So they have now said that for communities, they will offer for a fee to host solar on their rooftop so that your condominium or home or business doesn't have to have it on-site, but you have a share in that, and it's part of the purchase price, and when the home changes hands, it has to go with it. We and a group at UCLA are working with them to now say you could do storage off-site. And so that big storage battery, you could have an ownership share in that as well. And so this is not happening physically yet because it doesn't require to happen until the end of 2020, but it is where the rules are going to accommodate this difference. So it's an interesting, it's a big topic in California now.
Okay, so let's thank Daniel for an excellent talk.
Thank you.